So let me give you just this little table here. I've got a series of alcohols with increasing numbers of carbons to them, okay? Progressively longer carbon chains. And we're going to sort of predict solubility in water and solubility in hexane. Now, methanol, it's a small molecule. It has hydrogen bonding. Do you think it's going to be pretty soluble in water or not so soluble? What do you think? Similar intermolecular forces will cause things to mix together pretty well. Yeah, so it's going to be really soluble. In fact, so soluble that it is miscible. Miscible means there is no actual solubility value that they will combine together in any proportion. Okay? So whether it's 1% of one or 1% of the other or 50-50 or anywhere in between, they'll mix together really well. Okay? And in fact, that's the case for ethanol and for propanol. Okay? But the thing is, as the molecules get longer, we introduce more of that hydrocarbon style of a molecule that starts to become a little more difficult to fit in between those water molecules. Okay? If you think of water molecules, they've all got hydrogen bonding. They're attracted really pretty strongly to each other. They have no problem fitting methanol or ethanol molecules in between them because they can still have that same hydrogen bonding. Okay? But as the molecules get larger, those big nonpolar kind of parts of them tend to interrupt more of the hydrogen bonds than they replace. Okay? So once we get to a certain point, we actually have measurable solubilities. Okay? 0.11, and this is moles of alcohol per grams of water. If you're ever comparing different substances, you have to use molar solubility instead of mass solubility because they have different molar masses. Right?
Is that a maximum then?
Mm-hmm.
Okay.
Yeah. The maximum you could fit would be 0.11 moles of that per 100 grams of water. So, how do you think the solubility of pentanol will compare with butanol if you follow the trend? It's going to be even less. Okay, we're going to fit 0.030. Okay. And it continues. The longer the chain gets, the less and less soluble it is. So we're allowed to flush alcohols down the drain that are of three carbons or fewer because they just completely mix with water. They're totally miscible with water and they're not hazardous. So methanol, ethanol, propanol, we can flush that down the drain as much as we want. As soon as we get to butanol, we treat that as a solvent and it has to be disposed of with the other solvents. So not with the water because it's much less soluble. Now, look over here, solubility in hexane. Which of these do you suppose is going to be the most soluble in hexane? Pentanol. In fact, pentanol is miscible in hexane, and it actually turns out that it goes all the way up to here, and it's not till methanol where it's no longer miscible. So it's kind of interesting. Ethanol and propanol will fully dissolve in water and will fully dissolve in hexane. Okay? And it's just because we have a molecule that's hydrogen bonding, but it also has hydrocarbon to it. Okay? And at some intermediate level there, you get something where it can dissolve in both. But do those general trends make sense, everybody? You can think of it as hydrocarbon character versus H-bonding character when you're comparing stuff like that.
So the only thing I have a question about is since H2O, well, now And hydrogen bonding is an OH bond. Is that hydrogen bonding?
Hydrogen bonding is the attraction between this H and the O of a neighboring molecule.
Okay, so there's hydrogen bonding in H2O.
Yep.
And in all of the.
Yep.
the
Yeah, all of these have hydrogen bonding. Yeah.
Okay. Sorry, but then within the hexane, though, that one doesn't have any hydrogen bonding.
No.
So is that why it's reversed?
Yep.
Because it's more about the dispersion forces.
Yep. It's all about the dispersion forces. So the thing is, when you have a pretty big hydrocarbon portion of the molecule, it'll fit in between the hexane molecules. Once we get up to here, though, there's much less hydrocarbon portion, so these methanol molecules would rather just clump together as opposed to being spread out in between the hexane molecules.
Okay.
Comparing these two ionic substances, I think this was something we talked about before. Sodium chloride is soluble in water because the ions that we're separating are Na plus and Cl minus. Calcium carbonate is insoluble calcium and carbonate. Why do you suppose it would be easier for water molecules to surround and remove individual ions from the solid in sodium chloride? And why do you suppose it would be more difficult for water molecules to surround and remove calcium and carbonate ions? Charges, yeah. Stronger ionic bonds. Okay. The ionic bonding in calcium carbonate is not accounting for size, just accounting for charge. The ionic bonding is 4 times stronger, okay? Because it's sort of the two charges multiplied. So those much bigger charges have ions that will be held much more strongly together, whereas single charges like that are pretty easily separated from each other. Those interactions, those attractive forces of those ions are pretty much replaced by the ion dipole forces of the water molecules surrounding them. But the ion dipole forces aren't strong enough for water molecules to surround those ions like that. So that's the typical trend in insoluble ionic compounds. They tend to have larger charges like that and stronger ionic bonds in general. Let's just really quickly talk about what happens energetically as something mixes. Solution formation can be either endothermic or exothermic. Some solutions, when you mix them, they get warm. I'm thinking of like diluting acid. Most acids, when you dilute them, it gets really, really hot. Sulfuric acid, if you're making dilutions of sulfuric acid, it actually has to be in an ice bath, otherwise it'll start to boil. Other solutions will get cold when you mix them. Ammonium nitrate and ammonium sulfate and things like that, you mix them up, it gets cold. That's because there are 3 sort of different steps that have to happen, and the way those add up sort of influences whether energy is going in or out overall. So, thinking of Coulomb's law, we should be able to think about the change in energy required in each step here. Okay? So, 3 steps to formation of any solution. We have to separate solute particles. Okay? The solute that's in there, those particles have to be pulled apart. Okay? Does that release energy, or does that take energy? Does that need energy to pull molecules apart? That needs energy. Okay, molecules with opposite charges don't just fall apart. They need to absorb energy from their surroundings. So that is a positive delta H, right, for pulling charges apart. Okay. Energy has to be absorbed by the system in order to separate any kind of charges. Right? What about separating the solvent particles? If we got water or stuff, the water molecules have to move apart to make room for the solute particles to go in between them. So what's the sign of delta H for separating solvent particles? Water molecules, for instance, are held together by hydrogen bonding. It's attraction of opposite charges, so Coulomb's law works the same way. Yeah, delta H positive again. Okay. So, separate the solute particles, okay, get them apart from the solid. Separate the solvent particles to make room for the solute. Okay. Then finally, mixing the solute with the solvent. What sign is delta H of that process? Negative. That's going to bring opposite charges closer together, right, through their attraction. Okay. So what happens is these three values are different for different combinations of solutes and solvents. Okay? When we were talking about the two ionic compounds, it's much more difficult to separate very strong ions. Okay? So it gets to the point where it can't even happen. There's not even enough energy in the solution for it to separate at all. Okay? Some solvent particles are, held together really strongly. It's going to take more energy to separate water than it is to separate ethanol or something like that, because water has stronger hydrogen bonding to it. The combination of the solute and solvent, that gives you some energy back because it's a new attraction. It's going to be even more favorable if there's a really strong attraction between solute and solvent. You'll get more energy back. But you can see how these three things can balance different ways to make some solutions have to warm up to give off excess energy. Some solutions cool down because they need to bring in more energy from the surroundings for it to happen. So those relative strengths determine whether the process is exothermic or endothermic. Let me list for you some observations, and we'll predict the sign of delta H then for each of these processes. The observation for copper sulfate solid dissolving is the solution warms. The solution warms up. Is the overall delta H of that going to be positive or negative? Negative. Delta H is negative. When the solution warms up, that means the system had to give away excess energy. Okay? It's always, that delta H is always in terms of the system. So if the system is giving away excess energy, that's a negative delta H. That excess energy will go to warming up the surroundings. Okay? So in this one, ammonium nitrate, dissolving it, the solution cools. So that is a positive delta H. The reason a mixture would become cool would be if the system is sucking that heat energy into it. So delta H is plus, means the system is getting more energy, but it's pulling that energy from the surroundings. That's why the surroundings get cooler. Okay? So this is difficult to predict just from their formulas. There are ways of calculating it, I guess, that gets really kind of complicated, but it ends up being a little too complicated. So we just, as long as you understand these three processes, how they sort of combine together in possibly different ways to make a different result. We tend to think of solution formation as just a solid, we get a solid in here and then it just falls apart and then it's dissolved. Okay? But really, solution formation is a dynamic equilibrium between the opposite processes. So dissolution is solid dissolving, right? The particles on the surface of the solid breaking free from the solid and going out and being dissolved. That's dissolution. Deposition is dissolved particles that are floating around that land on the surface of the solid and get incorporated back into the solid. So just like when we were talking about vapor pressure, with molecules flying off and then landing, when we dissolve, it's going to be a dynamic equilibrium between those two processes. So what happens, obviously, when we have just pure water, we're going to have a lot of dissolution originally, okay? But eventually, as the concentration of those ions increases, we'll get more and more deposition happening down on the surface. And eventually, we'll reach a point where the dissolution and the deposition rate are equal. Okay? That's when dynamic equilibrium has been reached. And for sodium chloride, that happens at 36 grams per 100 milliliters. So a solubility value is essentially the amount, the concentration of that solute that you have that's dissolved at the point that the dissolving and the redepositing are happening at the same rate. Okay? So when that happens, it's called a saturated solution. Okay? And saturated solution is where the solubility is measured at. Okay? So when a solution is right at its solubility value, that's what we consider a saturated solution.
Solubility is per 100 grams or
100 milliliters, 100 grams? It could be either. I think it's usually per 100 milliliters, isn't it? Isn't that what we said before? Yeah, I only said 100 grams of water. It's going to depend. Yeah. That 36... That 36 value was specifically per 100 grams. So let's just be consistent, but yeah. We'll be a little more careful about that when we do a different kind of calculation there. But yeah, good catch. So the thing is, if we have a solution that is saturated, it's 36 grams per 100, okay, in terms of sodium chloride. If we dump in more solid, it's still going to stay at 36. Okay? You know, you could dump in more solid, it'll just settle straight down to the bottom. Okay? Once you reach sort of that upper limit of solubility, anything additional you add will just remain as solid. Okay? So, an unsaturated solution has less than the equilibrium amount of dissolved solute. So if we had 30 grams of sodium chloride dissolved, okay, the test is whether or not it would be able to accept more solute. So an unsaturated solution, if you poured more solute in it, it would dissolve. Okay? Saturated solution, if you poured more, it would not dissolve. Okay? Now, there is one special case of the supersaturated solution that's it's far more rare than either of these. Okay? 95% of the time, a solution will be saturated or unsaturated. Okay? A supersaturated solution is a special case, though, where it might temporarily contain more than the equilibrium amount of dissolved solute. So it is a disturbed equilibrium. Okay? It's essentially a solution that's not at equilibrium. So if we've been able to, say, temporarily dissolve more than 36, that solution will be supersaturated, but it's going to do whatever it can to get back down to the 36.
How would you do it, like increase the temperature?
Well, that's a clever idea, because solubility is dependent on temperature, much in the same way that vapor pressure was. part of the reason for this is the difference between those three delta H values of separation of the solute and solvent and recombination together. Most of them look like this, whereas we increase the temperature, we increase the solubility. So if we had something like potassium nitrate, where at room temperature it can hold like 30 grams or something like that, if we heat water way up to like 60, we could hold close to 100 grams. So you heat it up and saturate it at that high temperature, and then very slowly let it cool back down. It can cool back down to room temperature while temporarily keeping that extra amount still dissolved. Now you have to be careful that you don't bump it, or that no dust or anything lands on the surface, because any disturbance to that will cause it to rapidly recrystallize that extra out. So a solution can remain saturated, supersaturated indefinitely, as long as there's no place for those solid crystals to start forming. Okay? So that's why there's a really pretty neat demonstration. If this is a supersaturated solution, sodium acetate works really well for this. It will hold about 10 times as much at 100 as it will at like 20. Or water will hold 100. It will hold several times, 10 times as much more sodium acetate at 100 than it will at room temperature. So you heat it up to boiling or near boiling, you saturate it at that temperature and let it slowly cool back down, and we can have a supersaturated solution. But introducing any kind of point where the crystals can form. For instance, in this case, there's just a little solid crystal of sodium acetate on the end of that stirring rod, and if we just touch it to the surface, those extra grams of solid that don't really belong in there will very quickly recrystallize, and it'll sort of originate from there. Sometimes some will fall to the bottom, and it'll sort of grow from there. Eventually, the whole thing will sort of seem like it's overtaken by the solid that recrystallized out of that solution. There are actually really cool reusable hand warmers it's kind of a flexible plastic material. You sort of charge it by heating it in boiling water, but that supersaturates the solution. So then when you want it to warm back up again after it's cooled, there's a little clicker inside of it that gives the crystals a point to form on. So you do that little clicker, and you see it crystallizing out from there, and while doing that, it releases all that extra heat that it absorbed as it was dissolving. So they're cool. Search for reusable hand warmers. Yeah. Yeah. I got the solution. It's a pain to do though, because it takes a half hour to an hour or so to heat it up slowly and get it to dissolve, because you don't want it to boil because the water will evaporate and you won't go back. So you have to heat it up slowly, and then you have to let it cool even more slowly. If you just take it right off the heat and set it on the table, it'll just crystallize. So you have to let it cool really slowly and make sure you sort of tiptoe around it and no dust lands on it or anything like that. And you always have to make two of them, because you assume that one of them will get wrecked halfway between. So I think I recorded it at one point. So in our lab today, you are going to, I think you're using potassium nitrate. You're going to investigate. You're actually going to go the other way. You're going to heat it up and then let it cool and record the temperature where the crystals form, okay, for various concentrations of solution. So you'll be able to get a graph that looks something like that to form the solubility curve.
And what does that mean when the crystals form?
That means essentially that the solution is saturated at that point. It's no longer supersaturated. So temperature on solubility of a normal solid solute. Most of them get more soluble as you increase. Sodium sulfate is a little unusual. Sodium chloride only has a very minor increase and so on. So the effect on a gas, though, is a little different. As a gas is dissolved in a liquid, like just the oxygen in water or something like that. Okay? Let's see if we can figure out, will raising the temperature increase or decrease the solubility of that gas? So let's say you're heating a pot of water. Okay? You're going to make your mac and cheese or whatever. Well before it boils, okay, when its temperature is only about halfway up to boiling, what do you see on the inside of the pan? You see tiny little bubbles, okay, that go sort of all the way around on the bottom and on the sides. Okay? What do you suppose is in those bubbles? Yeah, it's nitrogen and oxygen. It's the dissolved gases that were in that water, right? The bubbles, but before boiling, well before boiling, that's the air that was dissolved in the water. Okay? And heating the water up has caused those bubbles to no longer be dissolved. Okay? So, go with that. Okay. Which bubbles more, or which doesn't retain its carbonation as well? So you've got a Diet Coke that you've opened that's nice and cold, one that you've opened that's at nasty room temperature. Okay? Which one is going to be nice and bubbly, and which one is going to be flat and yucky? The cold one will be bubbly because when it's cold, it's able to retain more of that dissolved carbon dioxide. As it warms up, it's able to hold less of that carbon dioxide, so that's why it would be. I mean, it gets flat over time anyway, but if it's warm, it's going to get flat a lot faster. So the general trend we see from both of these here is that as temperature increases, gas solubility decreases. And it's something like that. Oh. Okay. And that's going to be the case for every gas. That just has to do with the intermolecular forces and so on. As the molecules are moving, there's more of an opportunity for a gas molecule to make its way to the surface and fly off. And since it's a gas, normally it's going to be much less likely to settle back down and become redissolved again than it is to just fly away. This is why. This is, I guess, one reason why the temperature of the oceans is kind of a big deal. So, as temperatures increase in the oceans, they are able to hold less oxygen in them. So there have been places where there have been fish kills, big, massive amounts of fish that can't get enough oxygen because the water's too warm. It's warmer than they're used to. So this kind of thing has also happened around power plants. That's why power plants are very closely regulated as to the temperature of water that they can put back into rivers and streams, because if they heat up the rivers and streams too much, the fish can't breathe and suffocate. So heat pollution is an issue with that. The other issue with increasing temperature has to do with ocean acidification, and we'll talk about that a little bit later when we're dealing with acid-base equilibrium too. Okay? But that's an important relationship. That's pretty standard for any gas. So it's important you understand that relationship and how it's different than the way most solid solutes behave.